Hi, and welcome to Econ 480. These videos were recorded while I taught the class over Zoom, but they were edited so that the student faces, their questions, and my answers to those questions do not appear. As a result, these videos are going to be shorter than a normal lecture and then may have unnatural transitions. But I hope you enjoy them anyway. Bye now. I think we should get started. Today, we're going to have our second lecture, and it's just going to be more on linear regression. Um, so here the idea is that last class, here I have my recap slide. We talk about the interpretation of beta. We talk about three different interpretations: conditional mean expectation, a projection interpretation, and a causal interpretation. And then we talk about how we could solve for beta under the assumption that the expected value of xu is 0. Today, we're going to talk about solving and estimating for subvectors of beta. And then we're going to describe the properties, or at least the basic properties of the least squares estimator. Okay, so whenever I write LS here, that will stand for least squares. And then we're going to talk about the estimating beta. All right. So, do you have any questions that are hanging from last class? No. Okay. Good then. The vectors of beta. So we're gonna use the same notation we used last time. We're gonna have x, y, and u. Y and u are gonna be scalars, and x is gonna be a vector taking values in rk plus 1. And then beta is going to be in k plus 1, and it's going to be such that y is equal x prime beta plus u. Actually, I need to have my phone because I'm waiting for a phone call, perhaps, that I will have to pick up, but I don't want to see the screen, so I'm going to put it over here. And then we're going to partition x1, x into x1 and x2. X1 is just going to be an arbitrary partition. Okay, just let's split these variables into groups, and then we're going to let the dimension of those groups being x1 and k2. So the reason we do that is sometimes you run regressions and you have a bunch of variables in there, but then you may care about the effect or the covariate or the values of beta for some of those covariates and not for all of them. And so it is convenient oftentimes to just focus on the stuff that you care about. In this case, going to be just say x1, and then put everything else in some other group of covariates that here we're going to call x2. A very common case where this happens is, for example, as we move forward, where we have things like group effects or fixed effects or things like that that are typically in the regression because you want to allow for certain levels of heterogeneity, but typically are not the coefficients that you really care about. So by using this partition, we can write y equals as x1 beta 1, x2 beta 2 plus the same u. And then if we just use what we learned from last class, then we know beta is just x, expected value of x prime inverse x, y. And so now you just partition beta 1 and beta 2, and then you have exactly the same formula, which is expected value of x prime inverse expected value of x, y. But now it's just partitioned into these x1s, x2s that we see over here. So the question is, can we have a formula for beta 1 and beta 2 that admits some interesting interpretations, okay, if our goal is only to focus on beta 1? And the answer is just going to be yes, of course. And of course, you could do this by just using the formulas for partitions of matrices, okay? But, that is typically, just messy. It involves, dealing with formulas you may or may not remember. So I'm not going to follow that approach. I'm going to do something that is more straightforward, and that hopefully along the way of deriving this expression for beta 1, we're going to learn something along the way. But again, the goal is to see if I can find a formula for beta 1 that is cleaner than just saying just partition this matrix over here and you'll get what you want. All right. So in order to do this, I'm going to be using the best linear prediction operator that is associated with this interpretation 2 that we discussed last class. Okay. So just let me introduce some notation first. For any random variable A and a random vector B, I'm going to define the best linear predictor of A given B, okay, in the following way, which is exactly what we did last time. Remember last time was like X prime beta, where if you just project A on B, you're going to have B primes the corresponding beta, which is expected value of B prime, inverse expected value of B A. So one thing that I want to highlight here is that the best linear projection of A given B has only B as a random variable. But just look at the other objects, there are expectations, okay? So when you write best linear prediction of A given B, the only random element here is just going to be B that appears at the front of this expression, okay? And if A, instead of being a random variable, is a random vector, we're just going to use the same notation and understand this component-wise. So you're just going to do it element by element. Then we're going to define two random variables. Y tilde is just going to be y minus the best linear projection of y on x2. And x1 tilde is just going to be x1 minus the best linear projection of x1 on x2. So what we're doing is we're partialing out, and that's the terminology we're going to use, each random variable by x2. Okay, if you look, these are residuals, right? These are residuals. You just take x1 minus the projection of x1 onto x2. So this is a residual of our regression in the population level of x1 on x2. And then we're going to look at this regression that I wrote at the bottom, which is y tilde is equal to x1 tilde prime beta 1 tilde plus u tilde, where we're going to impose that the expected value of x1 tilde u tilde is 0. So, for example, we can do this if we, again, interpret this as another projection, like in the second interpretation of the regression model that we described last time. So there's not an assumption here. It's just that what we're saying, what's the interpretation of beta 1 tilde. And the claim, and this is what we want to show now, is that beta 1 tilde, the beta that you obtained from this regression at the top, which is the usual expected value of x1 tilde prime inverse expected value of x1 tilde y tilde, exactly the same as the beta 1 we had in the long regression from the previous slide. Okay? So if we prove this, which we're going to do next, then we're going to have some things that we can discuss about this that are going to be interesting. All right. So here I wrote down some basic notation. Remember the best linear prediction, and remember where we are calling this variable tildes. Okay. So let me now write the following. Beta 1 tilde is expected value of x1 tilde inverse expected value of x tilde 1 y tilde. And then what I'm going to do is to replace the y tilde variable. Is y minus the best linear prediction of y given x2. That's our definition of the tilde variables. And so this here is following. Just that, because expected value of x tilde 1 best linear prediction y given x2 is 0. Again, because the expected value of x tilde 1, x2 is 0. Why? Because x tilde 1 is a residual from the projection of x1 onto x2, and therefore, by the results of the previous class, is orthogonal to x2. And remember that this expression over here, whoa, that that's awful. This expression over here is only a function of x2, by what we saw before. The rest are all expectations, okay? So the first thing that we learn by looking at this expression over here is the following. A regression of the partial out x1 on the partial out y is the same as a regression of the original y on the partial out x1. So you see here that the only difference between the original expression here and the one that we obtain is that here we have y tilde and here we have y. So that means that projecting or partially out the y is irrelevant for this construction, okay? But this is not what we intended to prove yet, because we wanted to show that this is equal to beta 1, so we need to keep going. So what I'm going to do now is I'm going to replace y by what it is, okay? So let's write the beginning, expected value of x1 tilde prime inverse, and then expected value of x tilde 1, and then I'm going to write y as x1 prime beta 1 plus x2 prime beta 2 plus u. And then this is going to be expected value of x1 tilde prime inverse. And then we split the terms. Just going to be x tilde 1 x1 prime beta 1 plus expected value of x tilde 1 x2 prime beta 2 plus expected value x tilde 1 u. So we just replace y and then work out the terms. And then what we get is, again, this guy over here is 0 by the same reasons that I wrote before. x1 tilde is a residual from a regression of x1 on x2, and therefore it is orthogonal. And then this guy over here is 0 because in the original model we have expected value of xu equals 0, and x1 tilde is just a linear combination of the x's. So we put all this together, and what we have is that this is expected value of x1 tilde prime inverse, expected value of x1 tilde x1 prime beta 1. So we're almost there. So what I'm going to do is replace now the x1. And again, by definition, the x1 is just going to be x tilde 1 plus the best linear prediction of x1 onto x2 prime. And this is equal to the expected value of x1 tilde prime inverse, expected value of x tilde 1 beta 1, which is equal to beta 1. Because, again, expected value of x1 tilde, best linear prediction of x1 onto x2 is 0. And we're done. We proved that beta 1 that you obtain in a regression of y onto x1 and x2 is exactly the same as the beta 1 in a regression of y partial out from x2 onto x1 partial out from x2. And actually, in the middle, we'll learn that you don't need to partial out the y, so you can just do y onto the partial out version of x1. And both lead to exactly the same value of beta. Okay? Any questions about this? So notice that this is a characterization of the beta in the population. Okay. So what I wrote here is essentially what it just said. I'm going to read it. Beta 1 in the linear regression of y on x1 and x2 is equal to the coefficient in a linear regression of the error term from a linear regression of y on x2 on the error terms from a linear regression of the components of x1 on x2. Okay. And I wrote here, this formalizes the common description of beta 1 as the effect of x1 on y after controlling for x2. Again, when we start thinking causally about beta, and then we usually talk about these things that you're controlling for all this stuff. And then here you can see how you can actually formalize that mathematically by using this partitioning. Okay. And in the special case in which x2 is just a constant, which is the case that we are very familiar with, and then x1 is scalar, then in this case the projection is just the random variables minus their mean. So y tilde is y minus the mean, x1 tilde is just x1 minus the expected value of x1. And so it just, if you just apply the formula that we just described, you get with this familiar expression for this low parameter net regression, which is the covariance between x1 and y divided by the variance of x1. Okay, and if you use this formula, okay, to interpret, the coefficient of the random variable j, so just deduce is this variable by variable, what you have is that this lobe coefficient in a regression with multiple x's is just has the same representation as the one that you obtain in the case where you have only one covariate, except that now each of the x's first need to be partial out from the other x's that you have in the regression. Okay. But, if you just compare this expression with this expression, they essentially look the same. And so this way of working out this result gives us this nice interpretation of each of the coefficients or slope parameters that you obtain in a multivariate regression. All right. Questions? All right. So now we're going to talk about estimating this, guys. Okay. Because what we just did is a description of this result at population level. Now we want to see if we can use this trick to estimate betas by exploiting something like this. So we're going to partition x and beta as before. And let's consider the same regression that we had before. Y is x1 beta 1, x2 beta 2 plus u. And, for this result, again, I said, I'm not going to use matrix notation a lot, but in this case, it's just going to be convenient. So we're going to let, bold x1 to be the matrix that is n times k plus 1 dimension. And x2 is just going to be the same thing for x2. It's going to be n times k2 dimensional. And we're going to denote by bold P1 the projection matrix related to x1, and P2 the projection matrix associated with x2. In particular, I'm going to be using these two projection matrices, which are the ones that we describe at the end of the last lecture, which are what we call the residual maker matrices. Okay, they just take a random variable minus the projection on the other space. And in the case of M1, it's just the residual from a regression onto x1, and then M2 is going to give us the residuals from a regression onto x2. And we're going to let beta hat n be the least squares estimator from this regression here at the top. Okay, so these are the betas that we obtain if we just run y on beta 1 on x1 and x2 just by least squares. So I want to see if we can we can derive an estimation counterpart to the previous result. Okay, that is, we want to have an expression for beta 1 hat that we can claim that is numerically the same as running a simpler regression based on certain residuals. Okay, so let's look at that. This is a very famous decomposition. So I'm going to start by writing the model like this. Okay, so y is equal to x beta hat 1 plus x2 beta hat 2 plus the least square residuals. Okay, and remember that this matrix M2 is the residual matrix, residual maker matrix, okay, associated with the variable x2. So we're going to pre-multiply by M2, and so we're going to have this. So just pre-multiply by M2. And here we're going to use two results. The first one is that M2 times X2 is 0. Because this is essentially taking X2 on a regression on X2 and computing the residuals. Okay, so it's just a perfect fit. You're regressing the variable on the same variable, and that's 0 by construction. And then if you just don't see it, you can use remember the expression of this M2 matrix. Okay, and recall that is the identity, so that is X2 minus this P2 over X2. But remember that projecting X2 onto itself, it just gives us X2. Okay, so this is 0. And then here we have that M2 times U hat. Sorry, I forgot the hat. It's just U hat. And again, the reason is that this is U hat times the projection of U hat on an X2. Okay, but then this guy over here is 0 because the residuals are orthogonal to the axis by construction. And this is, again, a result that we saw in the previous class. So now this means that we can write then, based on this, M2 y equals M2 x1 beta hat 1n plus U hat. Okay. And so what we get now is we're going to pre-multiply by M2 x1 prime pre-multiply by M2. All right, so where was I? So we took this expression over here, and we're going to multiply by M2 x1 prime. So we have M2 m1 prime times M2 y, and then we keep going. We're going to have M2 x1 prime times M2 x1 beta hat 1n plus M2 x1 prime U hat. There we are. And then we're going to look at this term over here. This is just x1 prime M2 U hat. We just said above that M2 U hat just gives us U hat. So this is x1 times U hat. And we also said that the residuals are orthogonal to the covariates, okay, by construction. So that's exactly 0. And so now if we just use what we got, we have the beta hat 1n is equal to M2 x1 prime M2 x1 inverse M2 x1 prime m2 y. In other words, the same least squares coefficient can be obtained in a regression of the residuals of x1 from a regression of x1 on x2, the residuals, that x square, and the residuals from a regression of x1 on x2 on the residuals from a regression of y on m2. We just did the same as we did before, except that before we're working at the population level. Now we're working the sample and exploiting the properties of these projection matrices that we described last class. Questions? Any other question? All right, so we're going to start talking then about the properties of the least squares estimator. Okay, so let me recap what we wrote last time. Let yxu be a random vector where y and u are always scalar, x is k plus 1, beta is also dimension k plus 1. We're assuming that the first component of x is a constant, and we're writing the model like this. And the three basic assumptions that we described last class was the first one, expected value of xu is equal to 0. That's what we needed to get a representation that is consistent with least squares. Two is that the expected value of x prime is finite, which in words says that these variables x have finite second moments. And then the third one that we discussed is that there is no perfect collinearity in x. And then we showed this result that said that this is equivalent to say that the expected value of x prime, which is this matrix over here, is invertible. Those are our three basic assumptions to get results about least squares. And then we denoted by P the distribution of y and x. And we assumed that we had a random sample of size n from this distribution P that we're denoting y1, x1, dot, 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 yn, xn. The properties of least squares that we're going to discuss today are that the least squares estimator is unbiased under certain assumptions, that the least squares estimator is going to satisfy something called the Gauss-Markov Theorem. It's going to be consistent and asymptotically normal. And we're going to go through these properties one by one. We're going to start with bias. First thing is that we are going to replace our assumption 1 that said that the expected value of xu is 0 by this one that I'm going to call y prime, which is that the expected value of u given x is 0. And so essentially we're in the first interpretation of the linear regression that we described last class. And then if we assume this additional condition y prime, then we have this result that the expected value of the least squares estimator beta hat n is equal to the true value of beta. And this is what we call unbiasedness of the estimator. So I'm going to prove this. It's really straightforward. It's easier if we just write beta hat n in matrix notation. So I'm going to use it one more. This is x prime, x inverse, x prime, y. And then I'm going to replace y by what it is. So this is x prime, x inverse, x prime, x beta plus x prime, x inverse, x prime, u. So this is equal to beta plus x prime, x inverse, x prime u. So what I'm going to do now is I'm going to take the expectation of this estimator, conditional on all the x's, and this is equal to beta plus x prime, x inverse, x prime, expected value of u given x1, xn. And so this over here, if you view it element by element, just going to be expected value of ui given x1 dot 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 xn. But the data is IID, so the observations are independent across I. So this is same as expected value of ui psi, and this is 0 by our assumption u prime here above. And so we have that this is equal to beta. And so by the law of iterated expectations, since the conditional expectation is equal to beta, of course the unconditional one is also equal to beta. And that's the result. So all we use for this result is just writing beta hat in this form that we did at the top, which is typically convenient to work with this type of results. And then we just took conditional expectation. By taking conditional expectation, allow us to just bypass all this first part that only depends on x's, and then just obtain the expected value of u given the x's, and that's 0. Any questions about this? Then we have the Gauss-Markov Theorem. Here, to derive the Gauss-Markov Theorem, we're going to use 2 deviations from the assumptions that we had before. The first one, I'm going to use u prime again. U prime is that the expected value of u conditional on x is equal to 0. And the other one is we're going to add an assumption that I'm going to call 4 prime here, which is that the variance of u given x is sigma squared. When the variance of u given x is constant, I wrote here, and that means it doesn't depend on x, we say that u is homoscedastic, okay? And if that is not the case, we say that u is heteroscedastic. But for this result, we need this assumption, so we need to assume that u is homoscedastic. The Gauss-Markov theorem says the following. Under these assumptions, the OLS estimator is best in the sense that it has the smallest value of the variance of a prime y conditional on x among all estimators of the form a prime y, where a is just a function of the x's and satisfies expected value of a prime y conditional on x's equal to beta. Okay? In other words, we're saying if you look at all estimators that are linear, and by linear we mean a function of the x's prime y, and then you consider just estimators that have conditional expectation equal to beta that are conditionally unbiased, then we have that the least squares estimator is the one that will have the smallest value of this conditional variance. And smallest here, I wrote, is understood as the partial ordering, okay, where if you take, since this could be matrices, you say B is greater than B tilde if B minus B tilde is positive semi-definite, okay? Notice that this class of estimators includes the least squares estimators special case just by taking a prime equals to x prime x inverse x prime. That's exactly the least squares estimator, right? So if you just take here and use that particular a, you get x prime x inverse x prime y. That is exactly the least squares estimator. That will be our a prime here, okay? And this property is sometimes referred to BLEU, best linear unbiased estimator, okay? So notice that this theorem, I'm just teaching this here for the sake of completeness and covering all the finite sample properties. As a result, it's kind of like a useless result, to be honest, for multiple reasons. The first one would be that in order to claim this result, you need to impose these assumptions over here that are already stronger than the ones that you typically need to run regressions. And second, the result is just telling you that least squares is best among a very restrictive class of estimators, those that are linear and those that are unbiased. And why we care about that particular class of estimators is unclear, to the point that I'll say we probably most often probably don't care. But we're going to see the result anyway. All right. So we're going to prove this the idea is that I want to prove this theorem. In order to prove the theorem, I need to reformulate what we need to show. So let me do this first, and then we prove it. So remember, the estimator is a primes y for any function a of the x's, and it satisfies this condition that says the expected value of a prime y is equal to beta. So I'm going to work with this. Okay. So let me do this. The expected value of a prime y condition on the x's. I'm going to replace y. Okay. Is essentially a prime x beta plus expected value of a prime u condition on the x's. Okay. And this is just a prime expected value of u condition on the x's, which is 0. Okay, so this expectation over here is equal to a prime x beta, and it's equal to beta if and only if a prime x is equal to the identity. So that's the first restriction that we know this a should satisfy in order for this guy here to have conditional expectation being equal to beta. Okay? Otherwise, that won't hold. So that's the first element. We already learned that this a needs to satisfy that restriction over there. The second thing that I want to see is what's the conditional variance of this a prime y conditional on the x's. And then this is just going to be a prime, the variance of u given the x's, a, and this by our assumption is just going to be a prime a sigma square. Now note here that when a prime, this is awful, a prime is equal to x prime x inverse x prime, then we have that a prime a is just x prime inverse x prime x prime x inverse, which is just x prime x inverse. So the conditional variance for the least squares estimator is x prime x inverse sigma square. So what we want to show, I want to use this WTS a lot as we move along this class, which is want to show. What we want to show is that a prime a minus x prime x inverse is positive definite. So let's do that. So we want to show that a prime a x prime x inverse is positive semi-definite for any a satisfying this restriction over here, because this is what we have for the estimator to be conditionally unbiased. So we're going to define a matrix. Let me define the following. Let C, okay, this matrix C is just going to be A minus x prime x, sorry, minus x prime x inverse. And so now take what we want to show, which is A prime A minus x prime x inverse, and then replace A with this expression that we wrote over here. So notice this is going to be C plus x prime x inverse prime C plus minus x prime x inverse. And then we'll just work out the expression. It's just going to be C prime C plus x prime x inverse x prime C plus C prime x prime x inverse plus x prime x inverse minus x prime x inverse. So as you can see, the last two cancel out. And when you look at the other three terms, we know that here we have x prime c and here we have c prime x. Take either of them. Let's take c prime x. Well, this is a prime x minus x prime x inverse x prime x. This is the identity, and this is the identity as well, because of the condition that we derive for this matrix A that will require for the estimator to be conditionally unbiased. So this is 0. That means that this term over here is 0, this term over here is 0, and the entire expression is C prime C, which is greater than or equal to 0 by being the product of a matrix into itself. So we just proved the result. Just follow that the difference between the variance covariance matrix of any such estimator and the least squares estimator is always going to be greater than or equal to 0. So the least squares estimator is the one that has the smallest variance. And that's it. Any questions about this derivation? Consistency. So these two properties that we just described belong to the family of finite sample properties. Okay, they're properties that hold for any given sample size, and we didn't have to approximate anything. The last two properties that I'm going to discuss today belong to the family of asymptotic properties, and that means that we'll have to take the sample size to infinity. And something that we always need to remember, and these are things that I actually stress and cover in 481, which is a second year topics class, is that asymptotics are just to approximate finite sample objects. Okay, the goal or what we need is always a finite sample property, a finite sample object. Okay, it's just that we often don't do finite sample theory because we don't have the tools, because it's difficult, or in order to obtain finite sample results, you need to impose assumptions that are kind of unpleasant. So you work with asymptotics, and then the hope is that if one, your asymptotic tools are correct or appropriate, and two, you have a large enough sample size, then whatever finite sample properties of your estimators you have are going to be well approximated by whatever lessons you're learning from the asymptotic theory. Okay. If the asymptotics that you're using are poor, which is again not something that I want to describe much in 480, but it applies in other contexts. You need probably a more background to discuss that. But or if the sample size is not large enough, then these approximations may be poor approximations to what is actually happening, and so it's unclear what you learn out of them. In other case, we're going to describe them. The first one is called consistency. Okay. And it says, under our main three assumptions, beta hat conversions in probability to beta as a sample size goes to infinity. One thing I want to highlight here that as opposed to the other assumptions that we describe, consistency just follows from the three main assumptions that we described in the first class. We don't need to add anything special. And the proof is actually very simple, okay? Because I'm going to say by the weak law of large numbers, we have that these 1 over n, the sum from 1 to n of xi prime converges in probability to the expected value of x prime, which is finite by assumption. So we can invoke the weak law of large numbers. And again, by the weak law of large numbers, we have that 1 over n, the sum from 1 to n from xi, yi, converges in probability to the expected value of x, y, which again is finite by the same assumption that we invoke, which is, yeah. So then, since beta hat n is 1 over n sum 1 to n xi prime inverse 1 over n sum from 1 to n xi y, then this converges to expected value of x prime inverse expected value of x, y is beta by a continuous mapping theorem. And then we're done. So proving consistency is straightforward. Just follows, again, from the weak law of large numbers and continuous mapping by the fact that least square is just a continued function of these two averages. Yeah, because if you replace y, this is expected value of x prime beta plus expected value of xu. This is 0, and this is finite. So the same assumption 2 gives us that also expected value of x, y is fine in combination with 1, right? So this is assumption 1. And then assumption 3 guarantees that this guy over here, this inverse, exists. So we can apply the continuous mapping theorem. So here we use, if you want, assumption 3. And that's it. That's the proof of consistency. So then we have asymptotic normality. For asymptotic normality, we need the main three assumptions that we described before, but we need to add a fourth one, okay? And this is what I'm going to call assumption 4. Assumption 4 requires that the variance of xu, which you can write as expected value of x prime u square, is finite, okay? Before, remember that I defined an assumption 4 prime, that was our homoscedasticity assumption. This is not saying anything like that. This is just saying that this variance is finite, okay? No other thing. And so under these 4 assumptions, then we have that is square root n beta hat minus beta conversion distribution to a normal with mean 0 and variance equal to B, where B is this matrix over here that it has expected value of x, x prime inverse, expected value of x, x prime u squared, expected value of x, x prime inverse. And this is called a sandwich formula. And we have here the bread, then you have the meat, and you have the bread again. Okay, and that's the sandwich. Um, I didn't invent this terminology; it's used widely. Okay, and so we're gonna see as we move forward a lot of asymptotic variances that are gonna take this form. It's just gonna be bread, meat, bread, and then depending on the setting, the breads are gonna be different, the meats are gonna be different, but but you know, from a conceptual point of view, they're just going to have this same type of interpretation that I call it sandwich variances. So we're going to prove this. And again, first, I want to say, know that beta hat n is equal to 1 over n sum 1 to n xi prime inverse 1 over n sum xi y, and I'm going to replace the y, so we're going to have xi prime beta plus ui, and so just work this out. This is going to be beta plus 1 over n sum xi prime inverse 1 over n sum from 1 to n xi ui. And so by doing this, we see immediately that we can write square root n beta hat minus beta as 1 over n sum xi prime inverse 1 over square root n sum xi ui. And then the first thing that we have, which is the same that we did before, by the weak law of large numbers, we have that 1 over n sum from 1 to n of xi prime converges to the expected value of x prime, and then 2 by the continuous mapping, the central limit theorem, sorry, we have that 1 over square root n sum from 1 to n of xi ui converges in distribution to a normal with mean 0 and the variance of xu, which we assume is finite. And the result follows from continuous mapping theorem. Questions about this? All right. So we just saw in order to do inference, and by inference I mean, we're going to test hypotheses, build confidence intervals or confidence sets for these parameters. We will often require a consistent estimator of this asymptotic variance that I'm calling B here. And again, remember that it has this sandwich form, okay? So the bread, which is this part, is super easy because we already proved in the derivation that this object over here, 1 over n sum of x prime. Oh, and then here I forgot to add the p, that that this guy converts in probability to this expectation, which is precisely the expectation that appears in the expression. So we already know how to estimate the bread, and that's going to be the case most often. Estimating the bread is just straightforward. The part that is always more challenging, regardless of the setting, is the so-called meat, which is the middle of this expression. And in order to illustrate how we're going to estimate the meat, today I'm going to consider a very simple case, and we're going to describe the more general case in the second part of this class, okay? But for now, consider the case where we change two of the assumptions that we have. One replaced by 1 prime, which is the expected value of u given x is 0, and 4 replaced with 4 prime, which is our homoscedasticity assumption. The conditional variance of u given x is just sigma square. So under these assumptions, then this variance of x and u, which again we wrote here expected value of x prime u square, is just expected value of x prime sigma square. So, and in that case, if you just plug in that expression, you see immediately that the expression for b simplifies a lot, and it has two terms. The first one is the expected value of x prime inverse, which we already said is just the bread. We know how to estimate that. So the only issue is how we estimate sigma square. And so a natural choice for this estimator will be this object, which is the guy that we're using everywhere, times sigma hat square n, where sigma hat square n is a consistent estimator of sigma square. And if we do this, then we're going to have, by, again, continuous mapping, a consistent estimator of b. So we're going to do that. We're going to describe what this consistent estimator sigma hat square looks like. So a natural choice for this estimator is just 1 over n, the sum of the residual, the squares, and the claim here is that this estimator is consistent, okay? So we're going to prove that. So first, let's write the residuals. U hat I are just yi minus xi prime beta hat n. And what I'm going to do is I'm going to add and subtract xi prime beta, the true beta. So if we do this, we're going to have yi minus xi prime beta minus xi prime beta hat minus beta. And notice that this is ui. This is convenient because then we can write u hat as ui minus x prime beta hat n minus beta. So the first part of the trick is just to write the residuals in a way that make the residuals a function of u, which is the object we want. Then just take the squares. So if I take the square, then we have ui square minus 2 ui xi prime beta hat n minus beta plus xi prime beta hat minus beta square. Then first thing to note is that one over n sum from 1 to n of ui square, the true u, okay, converts in probability to sigma square by the weak law of large numbers, okay? And so that is saying that this first term here that we have is nice. So what we need to show, in other words, is that when we average the second term, okay, I'm going to call this A, and the third term, I'm going to call this B, that these are 0, okay? Let's see if that's the case. Let's start with A. So here we have 1 over n sum from 1 to n of ui xi prime beta hat n minus beta. And these are all scalar, so I can write beta hat minus beta prime 1 over n, the sum from 1 to n xi ui, and this converges in probability to 0 by the weak law of large numbers, okay, and expected value of xu0. So the second term, which I call A, converges in probability to 0 as we suspected or wanted. Let's look now at B. B, it's a little bit trickier, but let's just take the norm, the absolute value, 1 over n, sum from 1 to n of xi prime, beta hat minus beta, square. This is by the triangle inequality, less than or equal than 1 over n, the sum from 1 to n of the same guy. And this is less than or equal than 1 over n, sum 1 to n of xi square times beta hat n minus beta square. And so this converges in probability to 0 because expected value of xi square is finite, and beta hat minus beta converges in probability 0. And we're done. In this homoscedastic case, then, using this estimator of sigma square, which we denote here sigma hat square, just the average of the residuals square, is consistent for the variance of the true error term u. Okay. Any questions about this? All right. So what happens if we do not impose the homoscedasticity assumption? If we just don't want to assume this, okay, then, what I'm saying here, a natural estimator, which again, these are the estimators where you just grab any expectations that you see and you replace with sample averages. Plus, here you have the issue that you don't observe the u. So instead of using the u, you're just going to use the u hat. Okay. This is the so-called, heteroscedasticity consistent estimator, or HC estimator. And later in class, in the second part after the midterm, we're going to prove carefully that this estimator converges in probability to B, so that is, it is consistent for the object that it intends to estimate. Okay, and it only requires the assumptions 1 to 4 that we described before. And that is important because the same assumptions that gives us asymptotic normality are the assumptions that allow us to claim that this estimator of the variance covariance matrix is consistent. So later on, when we want to prove that certain usual t-tests and stuffs are, have the properties that we want, we're going to be able to derive that, but just using these assumptions 1 to 4. Okay. And this is sometimes called like white standard errors or Hoover white standard errors. And so they have different names. In general, we're just going to call them heteroscedasticity consistent. And then when you construct t-tests later on, as we're going to describe briefly next class, we're just going to take the diagonal elements of this matrix as the variance or the square root of those elements to get these standard errors. What's important, and I want you to just keep in mind, is that software like Stata and R still report by default the standard errors under homoscedasticity, which to me doesn't make any sense that in 2021 we're still getting this, but both of this software still do this. It should make a lot more sense that the default is to report something like this. And then if you want to add additional assumptions, that you can get the homoscedasticity only standard errors. But just be aware that whenever you get numbers out of this software without including additional options, you get this by default. Of course, those of you, for example, that are Stata users know that if you just go comma robust after your estimation, you're going to have at least a version of this type of standard errors, because they have sometimes some finite sample corrections and the like, with some constants multiplying this at the front. But roughly are going to be these ones. And then R, it requires you to just run a post estimation command. So it's not that it is difficult to obtain these standard errors. It's just that it is funny to me that you still get the homoscedastic only by default, because it's unclear why would somebody want to use those. But that's what it is. As long as you know the numbers that you're getting from the software. All right. So any questions about estimating B? All right. So we're getting to the end. So we're going to finish earlier today, and that's good news. So measures of fit. I'm going to just cover one slide saying that it's common practice to report measures of fit, particular this one known as the R square, which is the ratio of the so-called explained sum of squares over the total sum of squares, or you can rewrite this as 1 minus the sum of square residuals over the total sum of squares. And all these sum of squares are over here. The total sum of squares is just the sum of y minus y bar square. The explained sum of squares is the same with the y hat over here as opposed to the y. So this is essentially what the x's are giving us. And then the sum of square residuals is just the sum of the square residuals, as the name says. And so R squared is just going to be 1 if and only if the sum of square residuals is 0, or if you hat is 0 for all the observations. The S squared is going to be 0 if the explained sum of squares is 0. So that is if, your model is giving you y bar as the prediction, you're not having any x's, or the x's are just so bad that not explaining why that this is what's going on. And one interpretation that sometimes people, or variation that people use that you can get by giving some interpretation to this object is the following. Suppose that you view this total sum of squares as an estimator of the variance of y, and then you view the sum of square residuals as an estimator of the variance of u. Then the R square, may be viewed as an estimator of 1 minus the variance of u divided by the variance of y, which is sort of like the population analog of this object over here. And so when you look at things this way, is instead of using these estimators have 1 over n and 1 over n over here, you use their unbiased counterparts, that will be 1 over n minus 1, and here 1 over n minus k minus 1. Then you just write it like this, and this is known as the adjusted R square. And the adjusted R square has the property that whereas the R square always increases when you add more regressors, the adjusted R square may not. Now, these are called measures of fit, and that's what they are. They're nothing like that. It just tells you as a fraction how much of the variation of y you're explaining with your model. The fact that the R square is big or small or whatever doesn't tell you anything about how good or trustworthy your results could or should be. Because, for example, suppose that you have a model, you have some causal interpretation, and then you want to learn about the effect of some x on the y's. Then you can learn that effect while having a very small R square. So if you want a poor fit, because there are a lot of other things that you're not accounting for, and that may certainly happen, and you can actually obtain the same effect by adding, say, more stuff that will lower the variability of y and have a high R square. So whether the R square is high, low, whatever, is completely unrelated to whether you should feel comfortable or not where assigning, say, a causal interpretation to your model. But sometimes people care about how much of the variation of y you are actually explaining. And for that, this is what essentially R square is giving you. So that's about it for today. Are there any questions about this last slide or any of the other ones that we described today?